Here we're going to look at question 1 from section 2 of the ENGAA specimen paper. In this question we're given the following wave, which is a single frequency and a speed of 60 centimeters per second. We're told that for every single particle along a point on the wave, it takes 0.2 seconds to move from the equilibrium position to the next maxima or minima position. Then the question asks us, what is the wavelength of our wave? If you would like to have a go at doing this question, then please pause the video now, otherwise let's have a go at doing it. Okay, so to try and find the wavelength, let's think about some equations which have the wavelength in them. So the basic one when it comes to waves is probably this one, that the speed of a wave is equal to its frequency multiplied by its wavelength. Now this equation actually is going to be really handy here because we have the speed, 60 centimeters per second, and we have a wavelength, we don't have a wavelength, sorry, but we're trying to find the wavelength, so this is what we're looking for. However, we do not have a frequency. So how about we try and see if we can find the frequency of our wave from the information we were given. So to do this, let's again think about some equations to do with frequency, or what frequency actually is. Now frequency is just going to be 1 over the time period of our wave. So let's have a think if we can find the time period from any of the information which we've been given. Now it's obviously not going to be to do with the speed, since that's coming in as c. However, our other bit of information, our 0.2 seconds, might help us out. So we know that it takes 0.2 seconds for a point on our wave to move from the equilibrium position to the maxima. It's then going to take 0.2 seconds to move back, another 0.2 to move down to the minima, and another 0.2 to move up to the top. So this 0.2 seconds is actually going to be a quarter of our total time period, the time it takes for the particle to oscillate fully and then back to equilibrium. Therefore, the total time period of our wave is just going to be 0.8 seconds. So what we can do is we can substitute this 0.8 seconds into our equation for frequency. We find that the frequency is 1 over 0.8, which is just the same as 5 quarters of a hertz. Or if you do prefer, you can keep that in decimals as 1.25 hertz. So now that we know the frequency, which we just found, and we know the speed, we can go ahead and find the wavelength. So if we rearrange our equation for the wavelength, then we find it's the speed divided by the frequency, and then we can substitute in the values which we have. So converting our 60 centimeters per second to 0.6 meters per second, and substituting in our 1.25 hertz, we can find our wavelength. Now I prefer to work in fractions generally, I think they're a bit easier. So here I've just converted the speed into fractions, it's 3/5, and our value of the frequency is just 5 quarters, so because we're dividing I've just flipped that to multiply. So the wavelength is going to be 3/5 multiplied by 4/5, which gives us 12 25ths of a meter if you like, which of course we can just convert into decimals to find the wavelength as 0.48 meters. So this is going to correspond with answer C.